Let's go through some of the examples to illustrate memory management in your programming language. Static memory is allocated by a linker and it persists throughout the life of your program. Remember, static variables, depending on whether this variable it is initialized or uninitialized, is stored in a various different memory compartments. This static variable is not in heap or stack, making this static variable sort of quote unquote globally accessible. You can think of this static variable as a global variable now because it could be retrieved and stored in a different memory compartment. Therefore, a lot of times when you see static, namely static variable, static function, static methods, they are usually used in the context of global scope. And there is only one instance of this static variable, methods, or function. And their scope persists throughout the life of your program until you end your program shutting it down. Otherwise, most of the other variables, when declared locally, they are sitting on what's called your call stack. And these are statically allocated member variables or local variables. They go through what's called the push and pops, LIFO stack, one at a time, and they are managed accordingly. And this operation, push and pop in a LIFO fashion, is very, very fast and efficient. So most of your variables are managed this way on the stack without dynamic memory allocation. Let's talk about dynamic memory allocation in the next example. Dynamic memory allocation involves pointer in C++ and in C. Pointer is the concept of C, C++, not Java. As we alluded to, pointers is used to store memory addresses. You can think of a pointer as a data type or an object sitting in this memory cloud. Now, when you just declare a pointer integer extras I, for example, this is locally declared variable on the stack. So inside your stack memory footprint, let's say this area, your I sits right here. Just to illustrate, you can use size of integer start to print out the size of your integer pointer. This should give you 8 on a 64-bit computer. And because pointer has memory address associated with it, it may be considered as a data type. But it depends on whether this pointer is pointing to a string, float, double. The size of these pointers differ. Let's say we dynamically allocate a brand new integer on the heap and assign the address of that newly allocated integer to the pointer I that we declared earlier. Note that this dynamically allocated space is 4 bytes because the integer is 4 bytes. This dynamically allocated space on heap is located in this green box, and this 4 bytes sits in there where this new integer is located with, for the sake of illustration, an address FA2. This means that the integer pointer I now has the memory address of this newly created integer on the heap. When you see out I, the value of this pointer should give you FA2. As you will see later on, pointer could be used to manage data. Pointer can also be reassigned to track where the pointers are, and you can use pointer arithmetics to hop up memory locations and manipulate data by way of dereferencing a pointer, changing the values of those variables indirectly. So pointer is a very powerful tool in dynamic memory management. On the flip side, we have stack variables. This A sits on the stack. A is the variable of type integer. Integer has 4 bytes to it. When A is declared on the stack, the computer allocates this much memory to it. A is then assigned a value of 0 to it because we have A equals 0. This is done on the stack memory. There is no heap, no static, no BSS, no data. This concludes our discussion of memory management, illustrating the use of static, pointer, and stack variables.